You have fallen into Event Horizon with John Michael Godier. John is joined today by Aster Taylor and returning guest Darryl Seligman. Aster Taylor is a graduate student at the University of Michigan Department of Astronomy and a 2023 Fanny and John Hertz Fellow. Aster is interested in the dynamics of solar system small bodies, particularly their non-gravitational accelerations. They are also interested in the formation of giant planets and a myriad of other topics. Dr. Darryl Seligman completed his undergraduate degrees in mathematics and physics at UPenn in 2015 and his PhD at Yale University in astronomy in 2020. He was a T.C. Chamberlain Fellow at the University of Chicago Department of the Geophysical Sciences after completing his PhD. He's currently at Cornell and will be a Simonier NSF Scholar and NSF Astronomy and Astrophysics Postdoctoral Fellow with particular contributions to the Vera C. Rubin Observatory's Legacy Survey of Space and Time. One of the many problems we face when researching content for Event Horizon is the reliability of the news covering the topics we choose to feature. It can be difficult sometimes distinguishing real, verifiable science from sensationalized articles on the web. That's why we've partnered with Ground News, and we're excited by the fact that Ground News is a website and app developed by a former NASA engineer who worked on the New Horizons mission to Pluto. She developed the platform to give readers an easy and data-driven way to stay informed. Ground News gathers related articles from more than 50,000 sources around the world in one place, so you can compare original research and reporting with how outlets are covering it for a better understanding of the issue. Every story comes with a clear breakdown of the bias, factuality, ownership, and headlines of the reporting source, with ratings backed by data from 3 independent news monitoring organizations. Let's take a look at this story on how NASA astronomers have just detected unusual radio waves from space. Ground News found 28 sources covering this article. We can also see how credible each news source is, vital information for us, as it's based on how subjective or objective their reporting is. Comparing coverage, the differences are pretty clear. This source, like BGR, reports scientists scratching their heads, as there's no current explanation for what's going on, while on other outlets like The News are leading with these headlines. Luckily, Ground News always provides research to lean on, but they do more than create comprehensive story overviews. Our Vantage plan gets us access to their blind spot feed, which uses patented technology to help us easily step out of our own biases and see important news stories we might have otherwise missed. All of us at Event Horizon have been using Ground News as an essential tool in how we create the show. It's the first place we check for breaking news on space and science stories that we cover. Go to ground.news/Event Horizon or use the link in the video description to subscribe today. If you sign up through our link, you'll get 40% off the Vantage plan, which is what we use to get unlimited access to all their features. We think Ground News is doing important work, and we hope you'll check them out too.
Aster Taylor and Darryl Seligman, welcome to the program. Actually, welcome back, Darryl. You're always here.
Thanks for having me.
Thank you very much.
Now, generally, you have new work out that expands upon the idea of dark comets, and that we have these objects, potentially numerous, that sort of sit in a no man's land between comets and asteroids, which is an imperfect distinction in the first place. The lines blur. And here we are in the middle where you might have an object that can outgas volatiles, ice sublimating, and can cause accelerations in an object without ever seeing dust, which would be, your typical visible coma of a comet. Tell us more about the basics of dark comets.
Yeah, so that's a really great introduction that you just gave. We know about 7 of them right now. They're, like you said, they're these small objects that are in the near Earth environment, relatively close to the Earth. They don't have any visible coma. They look exactly like asteroids. visibly. They look a lot like near-Earth asteroids in their orbital parameters. But if you look at them over a decade or more, and you track their positions on the sky, they move in ways that you really can't explain except by non-gravitational accelerations. And then if you do even more work, which we did, of course, you can also look at the other mechanisms that should make asteroids move, and it's not consistent with any of those effects, the York effect, Yarkovsky effect, radiation, well, not York, Yarkovsky effect, radiation pressure, etc. And so the only real conclusion that we can make is that these are objects that are doing volatile outgassing that causes non-gravitational accelerations, but you can't see any coma on them. And so I think that's a good set of basics. There's a lot of mysteries remaining about these objects, but we've helped resolve those a little bit.
Now, with these objects, the non-zero acceleration, how long does it take to establish that that's actually happening? That you actually have a plot to show that this thing is moving, accelerating by a small amount, albeit, but accelerating, and is in fact not producing dust. How long does that take?
So the dust observations are much more specific because you just look at a usually optical image of the sky with a dark comet on it, and you measure the brightness from the center outwards, and you see that there isn't any fuzziness around the object, and so you see that there's not dust there. It takes a long time about a decade or more at least to detect the non-gravitational accelerations, just because number one, these non-gravitational accelerations are really small. And number two, it just the orbits don't change that much. I mean, what you're really looking for is it's moving from gravity. Here's where it should be, and it's at a different position from where it should be.
Aster, just to jump in,
Yeah.
and just as a caveat that Aster talks about in the paper, but the non-gravitational accelerations of the dark comets that we have found are really small. But that isn't to say
That's good.
that stronger non-gravs could be out there, like Oumuamua was stronger. Sorry. Yeah.
Oumuamua was much stronger, and that's why you actually observed a non-grav on Oumuamua, even though it was by definition only seen for a short piece of arc, right? It wasn't seen over 10 years; it was seen over 3 months. And the only reason that you can find a non-grav on that object is that the non-grav is so much larger. So for these objects, because the non-gravs are so small, it just takes a long time to observe them, 10 years or more. If the non-gravs were larger, we would have an easier time of it. But if there's a lot of complications about that.
Yeah, and then the fact, right, the fact that they're small, weird near-Earth objects that move really fast, so kind of counterintuitively, even if they have a orbital period of something like a year, it can go multiple orbits without even being observable from the Earth because the Earth has to line up, right?
Yeah.
So we're seeing apparitions sometimes every 5 years.
You don't see them constantly. So you're just seeing them every few orbits or more. So you'll see it over the period of a few months, and you're not going to see a small non-gravitational acceleration move it too much over a period of a few months. By 10 years, you'll start to see it, but you don't have to see it constantly because you'll see it for a few months, wait several years, see it again, wait several years, see it again, and it'll slowly progress from where you thought it ought to be. And that is your signature that there is a non-gravitational acceleration.
Now, this can do another dynamic thing with a we'll call it a cometary asteroid, a dark comet, and that is spin it up. In other words, over a long period of time, these objects can end up spinning very rapidly, right?
Mm-hmm. Yeah.
And that's a hallmark, maybe.
There are other mechanisms to spin up asteroids. It's a thing that most comets do. They will spin up once they're outgassing, but it's not a thing that only comets do. I'm not sure how commonly known the York effect is, but it's an effect that can spin up asteroids over longer periods of time than cometary outgassing, but it can spin them up. The measurements that we have for these objects, the rotation periods, also aren't observed over long enough periods to be able to detect a spin up. They're spinning fast, but we haven't seen them spin faster. So we don't know if they are spinning up from that outgassing. If they are outgassing, we expect that they should be. But they also just could be spinning quickly from some other mechanism, from the York effect, from collisions between other objects from a variety of factors that could induce more rapid rotations on just an object in general.
Although, like, even though it's, very smart to and responsible to say all of the caveats,
Yeah.
in your paper, there's a whole prediction of this predictive model, which is of the collisional cascade, which is at least consistent with.
Yeah, it's consistent with outgassing spinning it up, but we couldn't say that because they're spinning quickly, that implies that they have outgassing. We can say that if they have outgassing, that implies they should be spinning more quickly and spinning up. And there's a model that we've discussed in the paper that results from that assumption, from that logical inference. But it would be irresponsible to go the other way.
And say the name of it that you came up with, because the name is great.
Rotational fragmentation cascade?
Yeah.
Yeah, it's a fun name. The idea is just like, you get an asteroid, you spin it up, well, you get a dark comet, you spin it up from outgassing. It splits and it tears itself apart. The pieces are spinning just as fast, and they spin up, and then they tear themselves apart, and that just repeats as the outgassing occurs until you get the dark comets, or until they shred themselves into powder, or until the pieces just lose all their ices and just sit there as rapidly spinning normal asteroids.
Yeah, and Aster made a very, very beautiful figure that's in the paper that kind of gives a schematic overview of that cascade. But, it also, it is at least possible that larger dark comets are the progenitors of those small ones via this kind of
Yeah,
process that Aster outlined in the paper.
it's consistent.
Now, where are they coming from? If they're getting into the inner solar system, into the near Earth environment, and they're spinning and falling apart, where are they being replenished from?
Yeah, so not only are they spinning and falling apart, but the near Earth environment is just very unstable because you have the Earth, you have the other inner planets. And so objects can't last very long in that environment. And so that's another reason that they're removed and that they have to be coming from somewhere else. In this paper, we did some dynamical models and showed that most of the dark comets come from the inner main belt, from the inner edge of the main belt. And then one of them, the sort of odd one out, is probably from either the outer main belt, so towards the outside edge of the main belt asteroids, or from the Jupiter family comets that are orbiting near Jupiter. So there are these two different populations that we have in this paper, and the most interesting one I think is that the inner ones, the smaller ones that are not the odd ones out, are coming from the inner main belt.
Yeah, and just to kind of clarify one point about that, it's like that's a pretty different two source populations, because the Jupiter family comets,
Yeah,
those are the things that get kicked into the inner solar system from Jupiter that come from originally basically come from the Kuiper belt. So
yeah, there's a very, very different populations.
yeah,
But we can't make any strong conclusions about whether that one object
yeah,
is from the outer main belt, which is more similar to the inner main belt, or from the Jupiter family comets, all the way from the Kuiper belt. So
yeah,
we can say it's one of the two, but we can't say which one it is.
yeah. And these dynamical models, it's kind of statistical, because you've got to kind of fourth
Yeah.
grade huge populations and then kind of, say probabilities that they come from different places, but you can't figure out exactly where any given object came from. But what Aster's demonstrated is that, it does look like these weird, smaller, rapidly rotating ones, or these inner dark comets. It does seem like they're coming from the inner main belt, and then that could kind of point to a much larger reservoir of things like volatiles and organics in the inner main belt than was previously thought.
Yet it's still somewhat strangely consistent in a way, because you might expect a main belt asteroid to be somewhat depleted in volatiles, but maybe not completely, because it's got soil and everything else. Some things can hide and not really get sublimated, and then they do, especially if they start coming nearer to the sun than they were. So there is a certain interesting consistency here that I'm starting to see.
Yeah, and there have been papers published since the 80s looking at the preservation of volatiles in the interiors of main belt asteroids that showed that you can do it. there can be ices living in the interiors of main belt asteroids for the lifetime of the solar system up till now, which implies that they could exist. Obviously, it's hard to find because they're not on the surface, but this is some decent evidence, given that we have objects that have volatiles and that are from the inner main belt, that that population exists. There's also a sort of further bit that makes it weird. It seems perfectly reasonable, and it is reasonable, that asteroids can preserve ices in their interiors, but they can't form ices in their interiors, and they can't form ices where they are right now. The inner main belt is inside of the ice line, where ices will actually condense out of the massive disk of dust and gas that formed the solar system. And so any ices where the inner main belt is right now can't have been formed there. They have to have been formed outside that ice line and then moved inwards by some dynamical mechanism. And so even though it's perfectly reasonable that those ices are preserved and it's perfectly consistent, doesn't make anything weird, it does have implications for the planet formation for the solar system formation, for solar system formation in general, because it implies that there has to be some mechanism that has moved however many asteroids there are from outside the ice line to inside the ice line, where they stay right now in the inner main belt.
Yeah, I mean, Aster, like, you totally hit the nail on the head on like the interesting ramifications. And John, we've discussed this on your show before, very similar lines of reasonings, how you can, even from maybe interstellar comets that get ejected, using their compositions and, things like the existence of hypervolatiles like carbon monoxide or water to kind of say from which ice lines or outside of which ice lines they formed at. So it's kind of a similar theme there.
Yeah, and also the detectability of gases. So if you could take a look at one of these candidates, it's not always easy to detect an outgassing, especially if there isn't very much outgassing. It's doing it just very, very slowly, right? So these things would just show what in previous years would have just been anomalous acceleration, but only because it's just below the threshold of what we can see or, what we can actually resolve, right?
Yeah, and like we still can't see. We still don't have any observations that show the gas or the dust coming out from these objects. It's very hard for us to see gas in general, just because it's so diffuse and thin.
Oh, and also, sorry, Aster, and also remember the like wavelengths. Like water's the main thing in comets, and like there's tons of water in the atmosphere. So really, to get you have to do for comets, you got to do space-based stuff like infrared to get water and CO and CO2. I mean, you don't have to, and there are like some daughter products that you can do from the ground. It's tough.
But yeah, it's really hard to observe gases from asteroids or comets in general. So we usually detect that sort of outgassing through the dust that comes with it. In this case, I mean, it's the non-gravitational accelerations are so small that even if it was very much like a comet and was ejecting the normal ratios of dust and gas, we still wouldn't be able to see the dust or the gas because it's just too far. It's too small and too dim. And so, in previous years, these weren't even necessarily registered as having an uncommon acceleration. They had orbits fit through their data with uncertainties in those. And what eventually happened was we got enough position data that the orbit gets significantly better with the addition of non-gravitational accelerations. And so there could easily be a lot more of these that we just haven't seen. You can't see the coma. You can't see the gas. You only find them when you have a long-term observation of the data over, a decade or more. And so we don't really know how many there are. And if they were larger, they might be more detectable. The non-gravitational accelerations, I mean. But as it stands, we're sort of doing our best to find more and sort of out of luck from the physics perspective.
Yeah, and Aster kind of like in their paper, you did the calculus. Well, okay, we tried to do as good of a job as possible based on
The numbers that we have.
data. Yeah, like it's pretty hard to say based on the discovery of these discoveries so far about comets. Aster did as responsible a job as scientists could do to try to say how many more of them are out there. But it's very uncertain because of several reasons, of several complications with the data. But
Yeah.
the one really exciting thing, right, you show is there could be a lot more out there.
Between 53 total to 6,350.
Yeah, that's in the current census. And then like,
And then you get more from Neo Surveyor and from LSMC and from all the new instruments that go online that find a ton more of these. And
you find you also just find like a ton of new objects. Like,
yeah, you find a ton of new objects. That's the big one. And then, decades later, you find out, oh, actually, some fraction of them were dark comets.
yeah, and I mean, maybe the really little ones, maybe those type of things have like much stronger non-gravitational acceleration. So there could be many, many more of these. And then, so that's that's kind of the one major exciting takeaway. And then, another exciting possibility is like if you think back to like early exoplanet discoveries, once you started finding some, they kind of start popping up everywhere. I have a feeling that something like that could happen.
Yeah, I mean, we know to look for them now, right? Like we weren't really looking for near-Earth objects with non-gravitational accelerations of the relevant size.
Yeah, because why would we? Yeah.
Because why would we? We don't know of any. That's weird. It'd be kind of weird if there were any. So we're just not going to look. So like all the search algorithms that people use to fit the orbits, they don't include non-gravitational accelerations. And it's fair. Why would you? You don't really need them for most of the objects. But for some of these, you do.
Yeah, I mean, and part of that history, like, I mean, we have co-authors on the paper like Davide Farnokia and Steve Chesley, who did like a lot of the pioneering work about like effects that Aster was talking about, like Yorp and the Yarkovsky effect and some of the early detections of those. So it's like, yeah, it makes sense. You then, then start nailing down the non-gravitational accelerations, and it's telling you about new processes in asteroids that are really interesting. And then it turns out, oh, there are these objects with even stronger accelerations that can't be explained by those. It's pretty exciting.
Spacecraft. So it would seem to me to be useful to go up to one of these objects with a spacecraft. We've been doing that with asteroids lately, and see what we can see close up. How helpful would that be?
Very helpful, for the primary reason that a spacecraft will have significantly more accuracy and higher sensitivities to the small amounts of dust and gas that these objects are producing. And fortunately, we're very, very fortunate that by sheer chance, the Hayabusa 2 mission has an extended mission, Hayabusa 2 Sharp, which is going to an object that happens to be a dark comet. It's a complete coincidence. They hit the target before we saw it.
Yeah. I think I mean, when we first wrote the paper, right, it was like KY26. I was like, that sounds familiar.
Yeah, it was a 2 Sharp target.
It's texted you. I was like, oh my gosh, this is actually already the target for extended heights.
Yeah, so it's the fastest, most interesting. Like it's the most rapidly developed. This is probably not true, but it's the most rapidly developed space mission to an object of interest. Between like the shortest time frame between learning that it was of particular interest and sending the mission. Because the mission was sent before we learned it was interesting. That's means the 1998 KY26. It has other interesting properties.
Yeah, I think the target, it was selected as a target, right? Like we shouldn't just, I mean, it's already a very interesting one.
It wasn't purely random, right? Like
yeah, it's like it will be the first time you go up close to, it's a totally different size regime than any of the other small bodies they visited, and it's very rapidly rotating. So that's and it's got a good shape model and everything. So
yeah, so there's other reasons that it was selected, but now that it was selected, we have the great benefit of also it's a dark comet, and we'll be able to take a closer look at the outgassing that comes from it and at the composition of this object, and we can learn a lot by getting up close, seeing images of the surface, looking at what's coming out of it, looking at the dust and the gas that are coming off of it, we presume. So yeah, that'll be really awesome. It'll be hopefully well after I finish my PhD. So it'll be in a while, but it's a space mission. You can't ask for much faster.
I think Aster's already got more papers than I had when I finished my PhD. So I think you could graduate pretty soon if you wanted.
That's true, actually, yeah. I have to finish classes first.
Now, in the data sets of Deep Impact and the DART mission, we're basically blasting a hole inside of an asteroid. Is there anything to look for there that might give hints about the nature of dark comets, or is it the complete opposite where it says these were not dark comets? There's nothing there, nothing like the objects that we have as candidates.
That's a very, very good question. As far as I know, none of the data from Deep Impact or DART has indicated that these objects could be dark comets. The primary indication that you get from that is just that they do have subsurface volatiles, the impacts weren't quite deep enough to expose them.
Oh,
So it puts an
Aster, I think, but the Deep Impact one, well, that was the Temple one, right? That was to the comet.
Was it Temple 1?
Yeah, I think so. Okay, Aster, totally right on the DART thing, but with the
DART doesn't get deep enough.
because Temple one, I think the Deep Impact mission was the one that actually exposed subsurface volatiles.
Oh, did it?
And then it was like kind of cometary activity driven by the impact, because that was what we used as a bunch of.
Oh yeah, that's Temple 1.
Yeah, it's the one we used as a kind of like a lot of motivation for when I wrote that kind of crazy paper about sending an interception mission to an interstellar object like Oumuamua.
Oh yeah,
Like,
okay.
if you impact it, then you can reveal a bunch of subsurface volatiles that weren't activated.
Yeah, my bad.
But like at the same time though, like Temple 1, I don't think was like, yeah.
Temple 1 was a known comet, but when that impact was made, I think.
But I think for sure, like you can use like lessons learned from those missions.
For sure, right? Like we've shown from Deep Impact that you can activate subsurface volatiles by hitting it with a spaceship. From DART, we've shown that the DART target doesn't have those too super close to the surface, but they could have even deeper subsurface volatiles that DART didn't expose.
It's totally true.
We don't know, like we can't really rule it out. We can say that it wasn't above however deep the DART impactor went, but we can't really make a definitive statement that there definitely aren't any subsurface volatiles on DART, especially because we only hit one of them, right?
Yeah. Another thing is that while serendipitously the target of Hayabusa 2's extended mission is a dark comet, their primary goal is not going to be to figure out what's going on with the dark comet. So we will serendipitously get a lot of information, but ideally we can kind of work collaboratively with JAXA and motivate even more scientific what word I'm looking for, Aster? Even more scientific rationale for the mission and motivation in general. But
it's very unlikely that they would do an impactor mission with Hayabusa 2 sharp.
Yeah, I mean, in their most recent publication, though, they do show that a possible, I forget the wording that they call it. They call it like, it's kind of like extended activity, so it's basically possible maneuvers, but not for sure. But they did demonstrate at least the feasibility of landing.
Oh, that's awesome.
And impacting.
So it's doable, but
yeah,
they might do it.
They might do it, which would be like amazing. Like, oh my God.
Yeah, that would be awesome. But we also don't really have to, hopefully, because there's currently outgassing happening, right? So we should be able to get information about the surface quantity of volatiles from KY26, just from Hayabusa 2 being there and taking photographs, without having to actually expose the subsurface, right? And we know it has outgassing, and we can see what sort of outgassing that is from Hayabusa 2.
Yeah, I mean, getting up close is still way better than what we've gotten. So it doesn't. Yeah, you're right. Yeah, getting a spacecraft up close that's millions and billions of dollars in cost still is way better. So we'll figure out the cause of the mystery, if it's still a mystery at that point.
Yeah, it is in several years. 2031, so.
2031, that's right.
Yeah, so 7 years.
But if we get something like JWST to look long enough at some of these dark comets, maybe when they're kind of closer in their orbits to the sun, it's very feasible that we figure out what's going on before then.
Yeah, quite possible. either way, it'd be interesting. There'll be a lot more information from Hayabusa too. So even if we already have a good idea for what's going on with the outgassing, etc., Hayabusa 2 will give us more information about what's going on there.
Yeah.
There's some stuff that you just can't get from JWST, right? Like surface composition, surface features, stuff like that.
Yeah, not to the same. I mean, certainly at least not to the same.
Certainly not the same level. So.
It's the same level as like, yeah, a camera right up close.
Yeah.
Now, in regards to the near-Earth nature of these objects, whenever we talk about near-Earth objects, that's when you start getting into the possibilities of getting hit by one, Earth getting hit. Is it possible that Earth has been hit by a dark comet in its past, and could that have been what killed the dinosaurs?
It's possible that the Earth was hit by a dark comet in the past, certainly, and we can talk more about this idea later, but there is an idea that something like the dark comets might have delivered the volatiles to the Earth that make up the oceans, which would require a lot of dark comet impacts. It is quite unlikely that a dark comet is what killed the dinosaurs. Number one, the Chicxulub impactor was gigantic, and Darryl, you can tell me if I'm wrong. I don't remember exactly what the Chicxulub impactor is suspected to be right now, because I know there have been debates back and forth, and I don't remember what the conclusion.
Oh yeah, I think I think it's pretty established that it was an asteroid.
Yeah,
but
there's not a lot of commentary material on the Chicxulub.
Yeah, I think I think like, we can't say anything about it. I mean, could speculate about a dark comet and the what's it called, the dinosaurs, but with forgetting about that event, it is certainly possible the dark comets had hit Earth in the past.
In the past, yeah.
I mean, we know that the Earth has been hit by asteroids in the past, and Aster just showed that a significant fraction of the main belt could be dark comets. So yeah.
Who knows, right? Like it could be a significant fraction of the near Earth objects could be dark comets.
Sorry.
Main belt, no estimation of.
Yes, you're right. I'm sorry.
You're totally good.
Running on sleep here.
You're fine. So certainly the case that dark comets may have hit the Earth in the past. I can't make any definitive conclusion that they have. I would be very surprised if they haven't, just because they exist and they're in the near Earth environment, and the Earth gets impacted by objects all the time over its long history. So be very surprised if that hadn't happened at some point, just by sheer chance.
Yeah, that's like there's really potentially interesting ramifications there, because there's all this. So we should add, John, we were just talking, you like to say a caveat on your shows that you're not a scientist, but you're a generalist following a lot of different fields. A caveat to what I'm about to say is that Aster and I are not geochemists and
certainly not
oceanographers, although Aster has done oceanography stuff. But we don't even know. It's still debated in fields like that how the Earth got its oceans in the first place, and
we think that the Earth got its oceans from some sort of impact or
right, delivered from stuff from the more outer solar system.
All right. We know it came from. We're pretty sure it came from some icy delivery mechanism. We don't know what population those ices were delivered from. And it is certainly possible that the dark comets play a role in that delivery, which would require an Earth impact. But because they have volatiles, they're in the near Earth environment. They're from a source that we haven't seen a lot of evidence before, which is the subsurface volatiles in the inner main belt. It's quite possible that the subsurface volatiles in the inner main belt are a somewhat significant source of volatiles that eventually were carried on objects that hit the Earth and then formed the Earth's oceans.
Yeah, and I mean, we know, just again, I guess I should say I'm also not a biologist, but I'm pretty sure that water is one of the essential ingredients for the development of life.
That's certainly, I don't think you have to caveat that with a biologist. It'd be wild if that wasn't true.
The universal solvent. But let me ask you this in regards to water delivery. And this actually gives me goosebumps, because this Darryl, you wouldn't go this far, but I'm not a scientist, so I will. Is that yes, water is needed for our type of biochemistry for sure. You need the solvent, and there aren't that many alternate solvents that life could arise in. There's a few, but they're not very common. Ammonia maybe, or an ammonia water mix. There's a bunch of ideas.
And we do use water. Like if we learned if early life was done in ammonia, it's a somewhat ridiculous concept to say that early life occurred with ammonia as a solvent, and then we transitioned to water.
No, there's no reason to suspect such a thing. It was water. It was water. It was our beautiful water, and delivered potentially by dark comets. Now, this tells me something, though. All right, Earth wasn't the only one that had water. Mars did too, and potentially Venus also may have been a water world, but that's a lot less clear. That's a whole lot of dark comets. So does the population of dark comets in a star system decrease as it ages? In other words, as these things outgas and move around and do their thing, do you end up with lesser and lesser volatile bearing objects? And that in the past, during the early solar system, when Earth's water was delivered, there was a whole lot more.
Yeah, I want to say, I just want to jump in because John, like that's a really clever point that we haven't even like Aster and I haven't even thought of and discussed, and I'm really, really curious to hear what Aster thinks right off the bat.
So what I'll say is probably you're not going to make more. So somewhat by definition, you're going to have to lose them. If there's a process to remove them, which there is, and there isn't a process to make them after the original disk goes away, then by definition the population is going to decrease. I don't know if there's a question about how fast it's going to decrease, right? There's a good argument that it will decrease by quite a bit, because in the early solar system, we are pretty sure you will have a lot more small bodies just around. The disk that formed the solar system has a lot more mass than is current, well, not a ton, but has more mass than is currently present. There's going to be a lot more debris out of that disk. And then as the solar system evolves, a lot of that debris is removed through dynamics, through various mechanisms. So I'm not sure. I can't make any strong claims about, the dark comets are removed by their outgassing. We don't know what they used to look like before they became dark comets. They may have been normal comets. They may have been normal asteroids with some ice in them. We don't know how common that is, and we don't know what caused these to become active now. But what we can say is they're small bodies. There used to be more small bodies. Presumably the case that we have fewer of the dark comets now, because I can't think of any particular reason that they would be spared from the general removal of objects. So basically, yes, like there should have been more dark comets in the past than there are now. And that population should.
Although, yeah, I mean, yeah, I think technically that's all right, but a lot of it. One thing unappreciated, I think, by a lot of people who don't study comets is that a lot of the work that goes into studying comets is a huge main goal is to try to figure out what is causing what we refer to as cometary fading. But that is what we say for when comets kind of fizzle out or whatever. And we don't even know. I mean, comets could die from lots of different effects. There's stuff like very similar to the rotational disintegration cascade that Aster was describing, which is comet spins up and disintegrates and then it's dead. Or
but even if it doesn't, we see the time.
Like, yeah, the depletion of volatiles, right? But then the thing is, like, all of those estimates are benchmarked to the number of comets you see, and we think they're coming from the much further out in the outer solar system. So it's also possible that the flux of the inflow rate into the inner solar system of the dark comets is kind of in a quasi-steady state and has been for a long time. So maybe there's a huge amount of
population, though, right?
hydrated, right?
The inner main belt. The inner main belt isn't getting replenished.
Right. So it's really,
That's primary.
well, John, hopefully you kind of enjoyed us like spitballing, but we didn't think about that yet. So we're just talking and this is like we're just having a discussion.
About it a bit in the past, but it's not. Yeah, it's also like it relies heavily on the question of what happened in the early solar system between the formation of the disk and now, right? How did Jupiter and Saturn move around? How much material was cleared out of where, et cetera, et cetera, et cetera. And those are very contentious questions in the community that I don't have a strong answer to.
Right. The details
are very complicated, and I don't have an answer, and nobody has an answer.
Yeah. Oh, people say, oh yeah, some people have answers, but people have answers that generate something that looks like the solar system, but there isn't like a definitive answer.
There's no definitive answer. And I would be confident saying that the number must go down.
Yeah.
Because you can't make them and you can destroy them. So the number must go down. The question of how fast did it go down depends on how fast you can destroy them and how many there used to be. And that's a question that relies a lot on the history of the solar system and on cometary fading and on activity and all those sorts of processes that we don't understand about other objects or the dark comets.
And like Aster, can you explain the like issue with the time scale?
Oh yeah. There's this problem that we can do that we calculate where it takes about 10 to the 8 years to remove an object. No, 10 to the 6 years. 10 to 6 years. It takes about 10 to 6 years to remove an object from the near Earth environment. That's about how long an object can live in the near Earth environment before it gets kicked out. And you can calculate about how heavy the dark comets should be and about how much mass they should be losing to explain their non-gravitational accelerations. And you can do estimates, and it takes about 10 to the 4 years for the dark comet to lose all of its mass to this non-gravitational acceleration. And that's a problem, because if they live for 10 to the 6 years, and if they can only be for 10 to the 6 years, but it takes 10 to the 4 years for them to be gone completely, that's somewhat implied that there should be about 100 times as many as you see.
Because, and the important point, sorry to jump in, Aster, like that 100 times is if it takes 10 to the 4 years to lose all its mass and 10 to the 6 years to get injected, then the fact that we saw these ones that are active now, it's got to be 100 times as many that are there and dormant, right? Because the idea being that, well, these things can't be outgassing at that rate their entire lives, so they've got to be only outgas. If it's a factor of 100 discrepancy in those 2 times, then they've got to be turned off for 100 times as long as they are outgassing, which implies that if we're not living at some special time, that there are 100 times as many dormant dark comets from wherever they're coming from.
And we also just have to care about like the number of objects should increase in general in the past. And this is I'm always a little bit I get worried about the 100 times ratio because the estimates that we make of the population in the near Earth environment is 0.5 to 60%. And 100 times either of those numbers is too big.
Yeah.
Like 100 times 0.5.
Yeah.
That's fine.
Yeah, no, it's worrisome because it's not worrisome. Aster's not saying, I don't want to speak for you, Aster, but it's like, I don't think we're worried because there could be 1,000% times number of dark comets out there. We're worried. It was like, what is it that we're miscalculating or not understanding?
What are we missing that, because we have these 2 relatively, as reasonable as we can make them, approximations. And if you combine them, you get an answer that's nonsensical.
Yeah, it's just bizarre and complex.
Has to be wrong, right? So the question is like, is that 100 times wrong? Can we make the lifetimes shorter for dark comets? And like the lifetimes in the near Earth environment, can we make them last longer with the outgassing? these are things we've thought about. We don't have a clear, strong answer, unfortunately.
Yeah, we don't have the answer. It's like we're both kind of trying to figure it out, but
Yeah, we're stumped on that.
yeah, we're stoked. Yeah, it's pretty embarrassing actually.
It is quite embarrassing, yeah.
Yes, I can't help but to think what the future of the dark comets will be, because the humans will eventually have turned them all into O'Neill cylinders and there won't be any left. Now, this is a question specifically for Darryl. I'm going to ask her, of course, chime in. Oumuamua really starts looking like this. That was the thing that really struck me when I was reviewing the materials for this, is that I was thinking, man, that looks a lot like Oumuamua's acceleration. It's elongated, it's got all of these weird attributes. So is it possible that we have found a viable origin or potential origin for Oumuamua?
Well, I mean, I think the way that I want to look at it is that Oumuamua was a fascinating object, and something that the person, so Marco Micheli is on the paper, but he's also he's a co-author of ours, and him and Davide were the ones who identified Oumuamua's acceleration. So he said that his favorite thing about Oumuamua was that it got all these people who didn't study small bodies to work on small bodies and bring different perspectives to the field. And he said basically, like, I mean, I was one of those people because had never worked on small bodies before Oumuamua, and I don't know if I would have. And he said that having all of the fresh perspectives was really helpful. So I think we have that to thank Oumuamua for, and then we also have because Oumuamua we found that it had a non-gravitational acceleration very quickly, but that was because also, like Aster said, everybody was looking at it and they wanted to point Spitzer and Hubble at it, but the moon was in the way. So they had to get its trajectory exactly right 30 days after they discovered it, or however many days exactly it was, I don't remember. But so they had Marco basically identified the acceleration, Marco and Davide did, and then they pointed at it, but then it's totally weird and bizarre. But if not for that object that everybody in the world was looking at, I don't know if we would have really identified all of these dark comets. So it's like, thanks to Oumuamua, we're now identifying all of these new interesting bodies in the solar system, which could tell us all about these processes that we don't understand, like cometary fading and how the Earth got its oceans. But no, I don't think the existence of the dark comets implies that we have a definitive origin of Oumuamua. Like, I think Jenny Bergner's theory makes a lot of sense, and now we realize that it's totally precedented in the solar system of small body population to have non-gravitational accelerations without dust coma.
That being said, the processes, I don't think the processes they look similar, that they both have non-gravitational accelerations with no dust coma, but the process that move like that is different from the process made of dark comets like that.
And there's some, yes. Yeah, so Jenny's theory, about which I guess me and her did a show about that. But Jenny's theory about Oumuamua, like, that process absolutely will not work on these small bodies, because dark comets, because Jenny's theory requires hundreds of millions of years of cosmic ray galactic exposure, which we don't have in the inner solar system. So if there even was radiolytically produced stuff in the dark comets, it would have been fried. So there's no way that kind of process would work for these dark comets. So I think we have Oumuamua to thank for showing us this entirely new way of finding activity in a potentially enormously widespread population of small bodies in the solar system. But I don't think they retrospectively clarify the mystery of that object. They certainly, at least I would say, how about this? I would say that they contextualize it.
I like that. They contextualize it. All right, gentlemen, we are out of time, and I can't wait to hear more about this, because it's always exciting when you find an object in the solar system that you had no idea existed 5 years ago. That's what I love about solar system science, and actually astronomy in general, is that we don't know everything that's out there that nature produces, and it's just fascinating when we come across something like this that just 5 years ago nobody thought.
And I think, once you find something cool like that, John, like, you basically
you
keep finding them, right? So I think we're going to have a bunch more of these things, and they're going to tell us a lot. And I'm pretty excited.
Yeah, they end up as ubiquitous. And I mean, how often has that happened?
Yeah.
You know, in the history of science, where you find something and then you find out that it's extremely common. And I would cite one huge example: helium. We didn't even know about it until we looked at the sun, and then we're like, well, then we find it on Earth, and now, you know, we fill balloons with it, and unfortunately waste it and make it more expensive. Anyway, thanks, gentlemen.
Yeah.
Thank you.
Thank you very much for having us.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.